Hey YouTube, John here, and today we're going to be talking about microwave ovens. Now I'm sure almost all of you have a microwave oven just like this in your home, but have you ever wondered how it works? Well, hopefully with the help of my willing participant here, I'm going to be able to answer that question for you. Now first, this is my microwave, and it's got a problem. See, whenever you turn it on, it does this. And that's not a good thing. But before I scrap it out and get a new microwave, I figure I might as well learn something from it. First, let's consider how a microwave oven heats food. It does this by using microwave radiation, which is radiation that exists right in this region of the infrared spectrum, between infrared waves and radio waves. When these waves pass through the microwave chamber, they produce an oscillating electromagnetic field. This is to say that the peaks of the waves hold a positive charge, while the troughs produce a negative charge. Because water is a polar molecule, with an electron-hogging oxygen atom holding a partial negative charge, and the less electron-hungry hydrogen atoms possessing slightly positive charges, it orientates itself so that its poles line up with the electromagnetic currents of the microwaves. But these waves oscillate at a frequency of over 2 billion waves per second, causing the water molecules to continuously flip their orientations. This extremely rapid flipping of water molecules causes the particles to move around really fast and bump into each other. This is what generates the heat in a microwave oven. But where do these waves come from? The answer lies in the mechanics of this microwave. Well, apparently these things are childproof, so I guess I'm just gonna have to show you a picture of what I was gonna show you. This is where all the magic happens inside a microwave. It's called the magnetron. No, not the Megatron. The magnetron. The magnetron is a high-powered vacuum tube that generates microwaves by using the interaction of a stream of electrons with a magnetic field. Here, I'll show you how it works. In simple terms, a magnetron is just a copper tube with a tungsten alloy filament in the middle of it, and a vacuum existing between the two. When the filament is heated with an electric current, electrons are transferred across the vacuum from the filament to the tube, but they don't move in a straight line. A magnetic field is also applied to the tube, which applies a force to the electrons and causes them to spiral outwards and spin around the tube. This is a great example of the Lorentz force in action. As the electrons spin out like this, they pass over small openings in the sides of the tube. This creates a similar effect to how you can create sound by blowing over the top of an open bottle. But whereas you blowing over an open bottle causes air to vibrate in and out of the bottle, producing sound, the electrons moving over the openings in the copper tube cause the electrons in the openings to vibrate in and out, producing microwaves. As if all this wasn't cool enough, here's an experiment you can do at home that actually allows you to calculate the frequency of the microwaves in your oven. All you're going to need is a piece of cardboard and some cheese. Okay, first you're going to take the carousel out of your oven. You won't be needing that for this experiment. I'm going to replace mine with this super awesome 500 milliliter beaker. Next, you're going to spread the cheese in your cardboard, nice and thick, just like this. And don't skimp out on it. You're doing this in the name of science, remember? Now that you have your cardboard nice and cheesed, and your carousel out of your microwave oven, I think it's time to pop this thing in. Now we gotta give it a cook time. 30 seconds will probably do. Sounds like it's done. Let's see what we got. Woo! Here we go. Okay. So what you can see here is that parts of the cheese look like they've been completely untouched, while other parts are completely melted. This shows that microwaves don't heat completely evenly throughout their chamber. That's why you have a heating carousel in your microwave, which keeps things moving through different heating zones. And what's more, if you actually measure the spaces between these spots of meltedness, you're going to find that it's about 6.2 centimeters in between each melted spot. That represents half of a wavelength of a microwave, which is actually surprisingly close to the known value. From here, you can actually use that number to calculate the frequency of the microwaves in your oven. This is done using the formula F equals C over lambda. Or more simply put, the frequency of the wave equals the speed of light divided by the wavelength. When our numbers are plugged into this equation, with 300 million meters per second being the speed of light, divided by 2 times our half wavelength, times 1/100th to get into meters, we get an answer of 2.4 gigahertz, which is only a percentage or two different than the actual frequency of the microwaves in the oven. Knowing that the actual value is 2.45 gigahertz, we can do a quick calculation showing that in our own homes, using nothing but cheese, we were able to calculate the frequency of the waves in our microwave oven to within 2% of the actual value. Pretty neat, huh? Well, I think that wraps up our lesson on microwave ovens. Subscribe to my channel if you learned something, and make sure to tune in for weekly videos.